First of all, I would like to thank the organizers for this opportunity, especially Professor Crespino. So today I shall give you an overview of my research work on black holes in equilibrium with synchronized bosonic hair. So the work I'm about to present appears in 3 different papers and was done in collaboration with my supervisor, Carlos Herdeiro, Eugene Radu, Carolina Benon, and Luís Crespino. So here's the outline of my presentation. So I'll start off by giving some motivation for asymptotically flat hairy black holes in general. So this will overlap a bit with Eugene's course. And then I'll focus in a particular family of hairy black holes with synchronized hair, which have been one of the main focus of my research. So I will describe in a nutshell the space of solutions and some of their properties. Then, since these hairy black holes may emerge dynamically from the growth and saturation of an instability, I will discuss, based on that, how hairy they can become, how hairy these black holes can be. After that, I'll move to a somewhat different topic, concerning the thermodynamic stability of these black holes, and I'll end with some short summary and some final remarks on future work. So let me start by giving you a short introduction to this topic. So as you know, the Kerr metric is the currently accepted model to describe the phenomenology of all astrophysical black hole candidates. And according to the Kerr hypothesis, these black holes have exactly the same space-time structure defined by the mass and the angular momentum. But could astrophysical black hole candidates be described by something else rather than the Kerr geometry, at least at some scales? And, well, at the moment, there is no clear tension between observations and the Kerr model. So one might think whether it was even worth it to raise this question. But the thing is that the limitations of general relativity and the standard model of particle physics push us to consider non-Kerr models, which possess new macroscopic degrees of freedom, and to assess how much we can distinguish them from the Kerr paradigm with current observables, namely gravitational waves and shadows. So to find non-Kerr black holes, one must either, as Eugene said yesterday, modify gravity and or include matter in the standard model. So here we shall be interested in an example within general relativity with matter beyond the standard model, namely ultralight bosonic fields, which have been proposed as dark matter candidates. And this leads us to black holes with synchronized hair. So these are stationary, asymptotically flat stationary solutions of Einstein's gravity, minimally coupled to a complex bosonic field with non-vanishing mass, mu here. And taking into account the range of masses of astrophysical black hole candidates, this mu, the mass, is very, very small, ranging between 10 to the minus 20 to 10 to the minus 10 EVs. So the field, as you can see, can be either a scalar or a vector, and is characterized by a phase angular velocity or oscillation frequency omega, and the number of nodes in the azimuthal direction, azimuthal index or Wien number, as you prefer. So these solutions form a family, a countable number of families, which are, So I forgot to mention that both omega and m satisfy this condition, the synchronization condition, which equates the oscillation frequency with the horizon angular velocity. And you may recognize this as the threshold of superradiance. So as I was saying, these solutions form a countable number of families with 3 continuous parameters: the mass, the angular momentum, and the Noether charge. And the families can be labeled with 3 discrete parameters: the number of nodes in the radial direction and the azimuthal index. Solutions with n equal to 0 and m equal to 1 are fundamental solutions. Okay? So this is the space of fundamental solutions with both synchronized scalar and vector hair. Okay? In this plot, the horizontal axis is proportional to the frequency omega, and the vertical axis is proportional to the mass. So you see that the hairy black holes populate this spiral-shaped region, which is bounded essentially by 2 lines. The solitonic line, which is the red solid lines here, describing spinning bosonic stars, and is also bounded by the existence line, so these blue dotted lines. There is another one here, it's not very clear. So this is the existence line of bound states between Kerr black holes and test bosonic fields. And these are commonly known as stationary clouds, and they are in a way analogous to the atomic orbitals in the hydrogen atom. So, sorry, I forgot to change the slide. So we've just looked at the fundamental solution. So let's have a look at one of the excited families of solutions. So if we inspect this plot, we can recognize 2 interesting features. So first, as expected, the excited solutions attain or have larger masses, okay? And second, the fundamental solutions exist for a larger range of frequencies. And this also seems intuitive because, well, a larger angular velocity is required for stationary equilibrium, right? For excited solutions to exist. And the same trends actually are found when comparing the fundamental solutions with both scalar and Procke hair. So you can see here that, in a sense, the scalar case is playing the role of the excited family. This is for the Procke case, I forgot to mention. So is replacing or playing the role of the excited family. So this is a manifestation here that of the well-known fact that the superradiant instability is stronger for the vector case. That's why the scalar case play the role of an excited family. Okay, so black holes with synchronized hair can be quite Kerr-like or strongly non-Kerr-like. And this follows from the fact that, as I said, they interpolate between Kerr black holes and spinning bosonic stars. And as an illustration of this fact, let's focus on 2 examples. First, we consider a fairly Kerr-like black hole. These are both examples refer to vector hair, but we could also look at the scalar case. So this is a fairly Kerr-like hairy black hole with about 10% of its mass and 40% of its angular momentum stored in the hair. And, well, this one obeys the Kerr bound. And second, we consider an example of a fairly non-Kerr-like black hole with about 77% of its mass and 98% of its angular momentum in the hair. So they are quite different, as you will see. So before that, sorry, you can say that the first one is well described as being a Kerr black hole surrounded by in this case, a vector cloud, right? And the second one can be thought as Eugene was saying yesterday, as a spinning bosonic star with a tiny horizon at the center, okay? So they are different in that sense. So we can look at some physical quantities for these solutions. For instance, the Noether charge density, which you can think of as the particle number density, is, for instance, I don't think you can see, but it's one order of magnitude larger for the hairiest solution, and it has a steeper profile. And this impacts on the Ricci scalar curvature, which measure the space-time curvature due to matter. You can also see that it's larger in magnitude for the hairiest solutions, and also the Kommer mass density and the Kommer angular momentum density are larger for the hairiest solution and have sharper profiles. So my point is that in the space of solutions of black holes with synchronized hair, you can have very different types of black holes. Some are very Kerr-like, some are very non-Kerr-like. Well, but we know that there are two, but some of these Kerr-like black holes can form, they have a dynamical formation mechanism. I said in the beginning that at some scales, some black holes with synchronized hair emerge dynamically from vacuum Kerr black holes. And this happens when the horizon size of a Kerr black hole is comparable to the Compton wavelength of the bosonic field. And when this happens, basically the Kerr black hole becomes unstable against superradiance, which results in a transfer of energy and angular momentum from the black hole to a bosonic cloud. And this was reported in a letter by East and Pretorius some years ago. So basically they found that at saturation, essentially all the energy and angular momentum has gone into forming this cloud. So in light of this, we can say that, or we can identify the proportion of energy stored in the hair with the efficiency of energy extraction from the Kerr black hole. But there is something we can tell right off the bat about this efficiency. So we know that Hawking's area theorem sets an upper bound of 29% for the efficiency of energy extraction from black holes. So in light of this maximal efficiency, hairy black holes grown from superradiance must have at most 29% of their energy stored in the hair, okay? But the thing is that the numeric evolutions by Easton Pretorius showed that only up to 9% of the initial energy is transferred to the field. So one might ask whether this value could be much closer to 29% or not. And the answer turns out to be negative, and let's see why. So in this process, the role of superradiant instabilities is basically redistribute the mass and angular momentum, splitting them between the trapped region and the hair. So this means that the evolution of superradiant instabilities is nearly conservative. And so the total mass and the total angular momentum are conserved, which leaves the reduced spin, little j, unchanged. Okay? So under these assumption, since Kerr black holes obey the Kerr bound, hairy black holes grown from superradiance should also obey this Kerr bound. So taking this into account, how can we get an estimate for the efficiency of superradiant growth? So we just scan the parameter space, so the space of solutions, looking for those with reduced spin less than or equal to 1. And this corresponds to this light orange shaded region here. This is for the vector case, but we get a similar picture for the scalar case. So you can see that it's a very, very tiny region, bounded below by the existence line and above by solutions with reduced spin equal to 1. So scanning this region, we can set an upper bound. Yes, so this is the existence line. This is the line with solutions with 10%, sorry, with j equal to 1. And so scanning this region, you can set an upper bound on the hairiness on P, or the efficiency of energy extraction, which is about 10%. And this is in agreement with the results by East and Pretorius. Okay. As for the scalar case, we get a similar result, but smaller, a bit smaller than 10%. And this is a prediction for similar simulations with a scalar field yet to be performed. So anyway, you can see that the two bounds appear not to be very sensitive to the spin of the bosonic field. Okay, so besides the nature of these hairy black holes, their dynamical formation, their hairiness, a number of aspects about these black holes have been explored in the literature over the past few years. But there is one that I'm going to talk about that hasn't been that much explored, and it concerns the thermodynamic stability of these black holes. So this is an off-topic here, in a sense. So to talk about this, I will first recall some conceptions about this. So in the 70s, Bardeen, Cartan, and Hawking postulated the 4 laws of black hole mechanics, and they noticed that the surface gravity and the area of a stationary black hole resembled the temperature and the entropy of in thermodynamics. So they realized at the time that that black holes could be seen or thought of as thermodynamic systems. So it is then natural to ask whether black holes are thermodynamically stable or not. And here I will restrict my attention to local stability, which concerns the response of a thermodynamic system to small fluctuations of, say, energy in the environment. Okay, so let me recall that a system is said to be in a local stable phase if any fluctuations produce a counteracting effect that ends up restoring the thermal equilibrium. Okay, so this local stability can be monitored by linear response functions, such as the specific heat, which is here written in terms of the temperature and the entropy of the system. So as you can see, since the temperature is positive, the sign of the specific heat can be inferred from the curve S of T, and this will be useful afterwards. So it is long known that the Schwarzschild black hole, the specific heat of the Schwarzschild black hole is negative, meaning it runs away from thermal equilibrium. But consider now a Kerr-Newman black hole that can exchange energy but not electric charge nor angular momentum with the environment, and this corresponds to the canonical ensemble. So as expected, there is a continuity with the Schwarzschild phase. I mean, the specific heat for sufficiently small charge and angular momentum is negative. But if they are sufficiently large, it becomes positive. There is a second order phase transition, and the black holes become stable. Okay, so this corresponds to these. So stable black holes are in this, fall in this gray shaded region. So this exhausts, in a sense, the description concerning electrovacuum black holes. So one might wonder if the same or a similar thermodynamic picture holds for these black holes with synchronized hair. Indeed, that seems intuitive. So what I want to know is if black holes with synchronized hair branching off from stable curved black holes are also stable, okay? And, well, by continuity, this appears to be, or one could think this would be the case, because that's precisely what happens in the Kerr-Newman family. So adding a little bit of charge to a Kerr black hole or a little bit of angular momentum to a Reisner-Nordstrom black hole, you see that the resulting Kerr-Newman black hole retains the sign of the specific hit. So let's see if that's the case here. So for that purpose, we choose, for instance, black holes, we choose black holes with constant angular momentum, right? That branch off from Kerr black holes which are thermodynamically stable. So these black holes along the blue solid line. And if we plot the entropy as a function of the temperature for these black holes along this dashed line, so these lines, dashed lines, are lines with constant angular momentum, okay? So if we plot the entropy as a function of the temperature, we see that it decreases as the temperature increases, which means that the specific hit is negative and the black holes are unstable, okay? So you can say that the addition of hair, the addition of a bosonic field spoils, and it's not clear why, but spoils the thermodynamic stability of the original Kerr black holes. And this is not exclusive of this family of black holes. So we found a similar behavior for scalarized black holes in Einstein-Maxwell theory, Einstein-Maxwell scalar theories, branching off from Reisner-Nordstrom black holes. Okay. So I'm now approaching the end of my presentation, so let me run over the main key points. So I presented several aspects of black holes with synchronized hair. They are a theoretical possibility of dynamical, robust, non-Kerr black holes that could appear at some specific scales of mass and angular momentum. So I showed you that they can be sufficiently akin to Kerr black holes, and this is important from an astrophysical point of view. And precisely these Kerr-like solutions form from superradiance with a hairiness up to 10%. But I would like to stress something here, which is this bound does not exclude the possibility of that hairier black holes can appear from another dynamical formation channel, such as the merger of bosonic stars. So it would be interesting to know how hairy these last black holes are. And as for the thermodynamic instability, we saw that they are unstable in the canonical ensemble, but this instability does not impact on their astrophysical relevance, because typically the time scale, its time scale is much larger than the age of the universe. But it would also be interesting to look, for instance, at the stability of these solutions in the grand canonical ensemble, which corresponds to the most general physical scenario. And I think this covers everything I wanted to say, so thank you for the attention, and I'll be happy to answer your questions.
So as per usual, so let's start with questions online. So anyone has a question for Nuno? Tá dando para ver aí, Jadir? Vai aparecer?
Acho que não aparece.
So any questions online? So if not, so we can have some time for questions in the local audience.
Thanks, Nuno. Very nice.
Hi.
What could be an ideal scenario to form a black hole, a hairy black hole with a very large hair? You mentioned that they may form during the collision of two boson stars, but the synchronization condition is quite special, no? In these orbiting boson stars, what could be an ideal scenario in which you may form these hairy black holes?
Hairier than this.
Yes, if it's not by superradiance.
If it's not by superradiance. Well, I'm not sure. About this bound, let me just say something, which is we assumed that the evolution of the instability is approximately conservative. At least that's what the evolutions by Easton Pretorius show. But if that conservativeness breaks at some point, maybe you could get hairier solutions. And also you have, although I think that's not possible, taking into account one of your papers with Carlos. So there is, these black holes, of course, are prone to their own superradiant instabilities. So one could say that via that instability, they could get even hairier and hairier. But apparently, as you argue in a paper, this instability has a time scale larger than the age of the universe. As for your question, well, since I'm not very familiar with this process, so the formation of black holes with synchronized hair via merger of bosonic stars, I won't say much about that. So sorry for the disappointment. But I don't know if you have any further question. No? Okay.
I think that is a very interesting problem.
Okay. But do you have any idea in mind?
No, perhaps it has to do with the frequency of the orbits of the boson stars that must match the frequency of the final black hole.
Maybe it would also be possible to form these solutions with a merger of a black hole and a spinning bosonic star. That would be interesting to see. So maybe if you choose appropriately the ratio between the masses of the two objects, maybe you could get a solution as hairier as you want.
But in that case,
this is
you
just
have
speculation.
a lot of loss of energy in terms of radiation. The gravitational cooling you lose a lot of scalar field. I think that is more related with the frequency.
Okay.
Instead of the mass. But it's,
okay.
Again, I guess.
Thank you.
So any further questions?
So actually, I was wondering about something that you just mentioned about the thermodynamical instability of scalarized solutions. Yeah. So those solutions are not unstable, mode unstable, no? Or
sorry, could you repeat?
So are those solutions linearly stable? Because usually the scalarized solutions are stable, and so that's why you call it scalarized, right? Because you have something that doesn't have any field.
From a dynamical viewpoint, they are.
So they are unstable or stable?
No, they are unstable.
Thermodynamically.
Yeah.
Okay. So they are unstable thermodynamically, but they are stable from a mode perspective. So if you search for modes there, you wouldn't find an unstable mode. So what does this tell you about the existence? So should I expect like a black hole there? Or?
It's not a problem because you see that Kerr black holes, which don't spin that much, they are unstable in the canonical ensemble, and still they appear to exist, right? So the key point here is that even if they are unstable, the time scale of the instability is much larger than the universe. Yeah.
Thank you.
Any further questions? So I have just one.
Okay.
Oh, sorry. No, I have just one comment. Do you think, because you talked about if there is a condition for the quantum wavelength of the field and the range of superradiance frequency for things to be formed dynamically, right? But do you know of any works about the spontaneous, so the quantum version of that? So you have the black hole, and it is coupled to a quantum field by, for instance, just the space-time metric, just minimal coupling, and so maybe there is a factor of spontaneous emission of quantum particles in the superradiant regime.
So you mean works about the dynamical formation?
No,
But no?
not
But
just
with quantum fields?
because I think there might be a way to understand this quantum mechanically instead of classically. So because for instance, if you look at basically what I'm going to talk about this afternoon is,
Yeah.
if you look at, yeah, so just a spoiler, right? So if you look at the Reiser-Nordstrom case, you have a spontaneous emission of scalar particles if they have a charge, and they are all the frequency of the modes are in the superradiant interval. Okay. But I think this basically it is a general property. So I think there might be some way of understanding things without talking about it classically, and maybe this tells us something about how to evolve a classical background into a classical plus quantum background.
Well, maybe there is a quantum analog of this, but I'm not well, I don't know of any work on that, but I'm not very, very familiar as you are with this type of works.
Yeah, but I don't think there are many
Okay.
works about that. So, but it's just a thing that occurred me right now. So, I think. Thank you, Nuno, and I think the last question of.
Thank you, Nuno. That was very, very nice. I just have a curiosity, because you were mentioning in the beginning the dark matter as candidate, as ideal. So you were mentioning a region of masses between 10 to the minus 10 to 10 to the minus 20. But then you said that in dynamical formation for superradiance, you want a Compton wavelength that is comparable with the sides, and that actually makes sense. But that field that you consider doesn't have a mass that is too low to have this kind of typical scale comparable with the scale of the black hole. Or you are looking at dynamical formation by superradiance for masses that are larger than 10 to the minus 10. Is this really a candidate for dark matter, the particle that you are choosing in here, or is just a proxy for having small masses scalar fields, if you want to see the...
Well, so regarding what I said, so basically, the dynamical formation happens when the mass of the black hole and the mass of the field is of order 1. So if you plug here the range of masses we know for the astrophysical black hole candidates, you get that range I told. I think some parts of this range correspond to real dark matter candidates, but please correct me if I'm wrong. So there is this paper with Eugene, Carlos, Philippe, with that lists a number of models in which this could happen. Okay. So yeah, I'm not sure. So if the well, I'm not sure now if I included here supermassive black holes as well in this range. Maybe I did. So maybe the whole range would be 10 to the minus 20. Yeah, I guess so. Because I think if you restrict to stellar mass black holes, you would get something like 10 to the minus 13 or 14 and 10 to the minus 10. Yeah.
Okay, thank you.
So any further questions? So if not, let's thank Nuno again for the nice talk.